Good morning. First of all, I would like to thank the organizers for the invitation. It's a great responsibility to open this meeting, so I hope I do it well. I divided this talk in two parts. The first part is some more or less old work that we've done and some other people, also on parallel between liquid crystals and cosmological defects. And the second part is the actual talk, which is about metamaterial modeling of space-time phenomena, including cosmological model called the Milne universe. So you all know the story, how it went. At the beginning of the universe, there was a sequence of phase transitions. And how I turn this on? Well, doesn't matter. So you have a great symmetry group, and with the phase transitions, a sequence of phase transitions that breaks symmetry and that leaves behind defects like monopoles, cosmic strings, domain walls, and hybrid defects as well. It doesn't seem to be working any longer. Maybe the batteries. Or I can use this. It's working now? Yeah, thanks. Okay, symmetry breaking is a well-known concept in physics. It's reduction of symmetry. So that happens in liquid crystals, for example. You have a high temperature isotropic phase, and you cool down to a nematic phase, where the molecules are aligned more or less parallel to each other. And then you can go further to another phase, in this case, this nematic phase. Again, you have a reduction of symmetry, as sketched above. And the consequence is the appearance of defects. I just put 3 of them here. This is a point defect, line defect. You can imagine this is copied in this direction along the 3rd dimension. And this is another one called texture, which is also a cross-section. I won't spend much time on this. And these are some old work, not by myself, but some other people. The first one's by Mark Bovic. I thought he was going to be here, but he's not. Originally, he was in the program, right? Okay, these are simulations of cosmic string formation in the early universe, in those phase transitions. And there are a lot of similarities, and some very good papers were written on the subject at that time, including from my colleagues in Maringá, where they verified the same kind of behavior of correlations, for example, in defect and defect in this case. Okay. I guess everyone knows what a liquid crystal is, but let me go quickly if someone doesn't. A liquid crystal is a liquid, not a crystal. And it may flow like a liquid, but the molecules are oriented, like in a crystal. So here are 3 examples of molecules. One is a rod-like molecule, a disc-like, and a banana-like shape. And of course, they'll be oriented in different ways, depending on the phase also. We'll be interested in this one here, the rod-like molecules. And for those, you can have these phases as example, the nematic phase, where the orientation of the molecules more or less parallel to each other. You have a chiral phase also. Just looking at it, you know why it's chiral. And it's metic one. And our interest is in this one, in the nematic phase. I'll briefly discuss how this is described by elasticity theory. You see three basic types of distortions in the liquid crystal structures: plate, twist, and bend, which are related to deformations like this. And each one contributes with a term to the free energy density. If you look at this, you have derivatives of n. N is the director. It's the average direction of the molecules. And of course, when n is uniform, constant over space, so this is 0 because you have derivatives everywhere. So, and since this is positive or 0, so this is an absolute minimum for the free energy. So the nematic phase, which is the aligned rod-like molecules, is the absolute minimum or the ground state of the liquid crystal. So defects are excitations of this phase, which correspond to local minima. And these are the ones I'm interested on. And if we consider non-chiral nematics, so that contribution to the free energy, this one in the middle here, disappears. And the free energy becomes simpler. We can assume a planar model where the director is confined to planes perpendicular to the defect axis. I'm thinking of line defects. And I can write in terms of this angle phi, which is just the orientation in the plane of the nx and ny components. So the only Lagrange equations corresponding to this free energy is just Laplace equation. And the solution to that gives the orientation of the director field, gives the defect solution. So if we look for singular solutions, there are two kinds, like in electromagnetism. In this one, n rotates as you move around. In this one, n rotates as you move away from the origin. B and D are harmonic functions. I don't care about them, so just forget about this. So I'm interested in particular in these solutions, which gives an integral like this. So if I forget this part, this is just a constant. So K is called the winding number and classifies the defect. So it makes, if it's a vector field, this is integer. If it's a direction field like we have here, it is integer or half integer number. Here are some examples of line defects. This is k equals 1. This is k equals 1 as well. The difference here is in the c, that constant that appears here, which is the theta equals to 0 orientation. So in this case, it's 0. In this case, is pi over 2. This is -1. This is -1/2. This is 1/2. The winding number, it's easy to find just looking at the picture. If you go around the defect, you follow the orientation of the molecules, and as you turn around by 2 pi, the molecule turns also by 2 pi. In this case, it goes in the reverse direction. So if you go counterclockwise, the orientation field goes clockwise, and that's why it's -1. And this is for the same reason, this is minus half and 1/2. Okay. You can do geometrical optics in the matrix of force. They transmit light. They are dielectrics. And these are very standard optics books, but just copying what it said there. The light rays can be obtained, the equation for light rays, from the Fermat functional, where here you have the effective refractive index, which when you have a molecule like this, you have two components for the index. So depending on the angle that the ray makes with the molecule. So you have two parts, so this is the effective index. So a comment in Born and Wolf says that light rays obeying Fermat's principle of geodesics in some Riemannian space. So this inspired Alain Jouet and Roland Ribotat many years ago to make a geometric model for the propagation of rays in an isotropic, homogeneous media. So they related isotropic to Riemannian geometry, as mentioned by Born and Wolf, and an isotropy they related to Finslet geometry, which is a generalization of Riemann geometry that includes directions. So it looks natural since locally you have directions for the orientation field. And after their work, we look at defects. They were not interested in defects in liquid crystal. They were interested in patterns coming from heat propagation and things like that. But then we used the same idea and explored a little bit the effects around line defects and like lensing and deflection of light in general. And more recently, Chiang and Lavrentievich used the same idea also to study propagation of light around line defects in a similar way. And this is an important, you see, you have people inspiring different people with this work. This is a sequence of inspirations. Jouet and Ribotat inspired us, who we all inspired Chiang and Lavrentievich, and by their turn, they inspired us for the work with metamaterials that I'll talk later. So for the line defects with this configuration, we found an effective geometry given by a line element. This looks quite ugly, but it has the ingredients that we have here. K and C appear here, and the ordinary and extraordinary refractive indexes, which are part of N, the effective refractive index. When they're equal, you have isotropic medium, and so you are back to the Euclidean line element. So anyway, for k equals to 1, you have that simple structure. And the effective geometry is conical. This is the metric of a cone. And light rays going on either side of the defect will deflect like this. This is working like a lens. It's a lensing effect. And you can see that on the surface of the cone. Same thing. What we're seeing here is like a projection of the cone on the cross section surface. So what's interesting here, and what is related to cosmological defects is this is just a section of the space-time of a cosmic string. A cosmic string is one of those defects maybe created at the beginning of the universe that corresponds to the same geometry. If you look here, it's exactly the same line element, plus you have time and z direction added here. Alpha here is called deficit angle, which is related, which has the same role as that one, is related to the mass density along the string, which is this mu. G is the gravitational constant. So, of course, we found that amusing and published that as analog of the cosmic string in liquid crystals. And maybe I should skip this or go very briefly. That's the same general metric. This is just the curvature scalar is obtained, but I want to show this part here. If k is equal to 1, the curvature scalar, the Ricci curvature, is singular at the origin. But if k is not 1, besides the singularity, you have something that goes like 1 over r square, rho square in this case. So this makes the defect quite different. So the question was, okay, if k equals to 1, we have a cosmic string. Can we have cosmic strings if k is not 1? So going back to space-time, we just use the two-dimensional metric we found for those asymmetric defects and add a z and a t axis, and so we have a four-dimensional metric. We use that in Einstein's equation for gravitational field and found the energy momentum tensor, which has a singularity at the axis, plus a distribution of energy or mass in space, depending on that. So we propose that there could be a family of asymmetric cosmic strings. Cosmic strings have not really been detected until recently. There are some images from a cosmic string that seems to be piercing a black hole in the center of a galaxy. So I should have put a picture. The picture is beautiful, but it's not really sure it's the cosmic string. So if maybe there are cosmic strings with k equals to 1, maybe also we can have cosmic strings with some anisotropy or some asymmetry. Okay, so partial conclusions here for the first part. The analogy between cosmic and thematic defects goes beyond the formation and evolution of dynamics. Those first papers that I mentioned by different people there studying formation, evolution, and the dynamics of cosmic strings. We're looking from the point of view of geometrical optics. Cosmological defects have been proposed inspired by their nematic counterparts. So we propose these asymmetric cosmic strings. And also the geometrical approach is very handy when it comes to the wave picture, because the boundary conditions are in the geometry. So you don't have to worry about that. And we made use of that by looking at diffraction of light by defects in liquid crystals. So the wave equation has to be put in covariant form. So you have to use it in the geometric background. Okay, so come to part 2. Yes. Sure, go ahead. Yes, yes. Right, right. Exactly. Mm-hmm. Right. C, right, right. C is just a choice for the axis and how you start to measure the angle with that axis. Oh, okay. No, it disappeared because I chose a particular one. Uh, let's see. This one. C disappears because I made it pi over 2. So from for the k equals to 1, yeah. But exactly, exactly. Right, right. But that's more sensitive to k, not as much to c, because you see here, uh, these in fact can be deformable into each other, but not these guys. Right, right, there. This one still has a C, and this one it's here. It's it's it disappeared, but it's not completely. Hmm. Um, in fact, there is only one kind of line defect that I know in cosmology, which is the ordinary cosmic string, which is that one given by this. So it's symmetric, and so it doesn't have the symmetry of the other defects. What in fact we proposed is that there might be some defects given by those values of k different from 1, and they would have a source given by this energy momentum tensor. But there's a problem with this, is that I'm giving a source, but I'm not giving the origin for the source. What kind of field you have that could originate this? The ordinary cosmic string can come from a U1 field, which could be just magnetic field. If you have a flux of magnetic field, and confined to a very small radius cylinder, it will give rise to this conic metric and space-time. But in this case, I don't know. I have no idea what kind of field would give this. So I'm not so happy with this work still because of that. I have a source, but I don't know what source it is. Okay? Okay. So let's go to this second part, which is so in the previous section, Fermat's principle was used to associate light paths to geodesics in effective remaining space. So we could use analog models to build curved space, but not time. Time still is an external parameter. This is okay for cosmic strings, but not for black holes or much else, because time is an ingredient of the geometry as well. So in this part of the talk, we'll see how time can be incorporated into the analog models so that an effective space-time emerges. Hyperbolic metamaterials will do this job. So just a brief introduction to metamaterials. They are highly anisotropic. Usually they are engineered, they are artificial, but there are some natural metamaterials as well, I will show in a minute. They have very unusual optical properties. They are essential ingredients for science fiction, like cloaking devices, perfect lenses, and so on. As you all know, dielectrics support electromagnetic wave propagation, light propagation, because of positive permittivity, but metals don't. You have the skin depth that prohibits the propagation through a metal. But we can imagine strongly anisotropic materials which may be metallic in one direction and insulating in the other directions. So for the electromagnetic wave, the material is neither metallic nor insulating. It's something else. It's a monster that allows some propagation. But for us, it's interesting to think of that. Along one direction, it's metallic, and the other direction is insulator. And what is more interesting is that they occur in nature. So, if you have an isotropic no-magnetic dielectric, permittivity is a tensor, and I'm supposing along these two directions the permittivity is the same, and in the third direction is perpendicular. So we have a dispersion relation for light propagating in this material given by a ellipsoid, in fact, in K space. But if one of these is negative, you have hyperboloids instead of ellipsoids. So something like this, you have two kinds of dispersion relations depending on your choice of the negative permittivity. So as the title of this article says, there are natural hyperbolic materials. Some appear in nature, or that can be artificially made. Like, for example, we have a dielectric matrix with metallic rods crossing it, or layers of dielectric and metal piling up like that. In this, there's another work. There's a list of natural hyperbolic materials, and there are two of them. The first two of them are work in the visible. Most of them are in the infrared or UV regions, including graphite. Graphite is a natural hyperbolic metamaterial, but for UV. Okay, you all know about extraordinary and ordinary rays, so I want to stop here by reference. But let me tell you how you can model time with metamaterials. So how time can be incorporated in the analogy of liquid crystal defects and cosmic defects. So the wave equation in an isotropic material, if say x and y directions have the same permittivity, E2, and in the z directions is 1. And so the wave equation is like this, but we consider E2 negative. And we multiply this by h bar and call this a mass, effective mass. what we get is Klein-Gordon equation for a particle of mass h omega over c squared. And z behaves like time. So light propagating in a hyperbolic metamaterial like this will describe Klein-Gordon particles propagating in two-dimensional space plus time. So that's the idea proposed a few years ago, but used by a lot of people so far. So if you have hyperbolic metamaterial, instead of making it to mimic flat space like this, you can use curved rods or curved surface here, and then you're curving space-time effectively. So by curving the hyperbolic metamaterial, you're curving 2 + 1 space-time. So we're losing one dimension here. So this is a phrase from Smolyanov's paper. When a metamaterial is built and illuminated with a coherent laser beam, the stationary pattern of light propagation inside the material represents a complete history of a toy 2 + 1 dimension space-time populated with particles of mass m star. This history is written as a collection of particle wood lines alike the time-like z coordinates. So this is from the article. What they do to simulate this is they make these half circles of different materials here, alternating metallic and insulating, so they get the effect of hyperbolic metamaterial, and they shine light from here, and they claim to see the world line of Klein-Gordon particles coming from the Big Bang. So that's their picture of the Big Bang, and so the Big Bang would be here, and this is a light cone, so the light paths here correspond to world lines of, see, this is Minkowski space-time, right? The time axis, the vertical one, in effectively. Okay, so we can use that for something else. There are some cyclic universe models. So the universe might not have a final end. It might restart again. And so we might have an endless repetition of big crunches followed by big bangs. So the universe at some point starts to contract and then comes to a singularity. And then a big bang happens and expands and comes back here and so on. So there's a danger in this because there's a transition from the big crunch to the big bang, and you have a space-time singularity. So what happens there? There are many ideas about this, and one possibility is that the singularity is the temporary collapse of a fifth dimension. So imagine that the space-time has 5 dimensions, and the extra dimension is circular. So that only dimension, this radius of the circle shrinks until it collapses to a point and then starts to grow again. The remaining of space-time stays as it was. So the three space dimensions remain large, and time keeps flowing smoothly, but you have a singularity caused by the collapse of that extra circular dimension. So this is a model in 5 dimensions, but you can reduce it to a 2-dimensional model. It's called the compactified 2D Milne universe. I won't give details of this, but it is a surface in 3-dimensional Minkowski space. In fact, it's a cone. And the question is, can we simulate the passage through the singularity in the laboratory? So as we saw, we can follow a Klein-Gordon particle in some exotic space-time. So why not in this one? So that's what we try to do. So this is the cone, And a cone in Euclidean space is defined in spherical coordinates by just taking theta angle constant. So the 3D line element becomes this, which is the induced metric of the surface in Euclidean space. But this is not very convenient because it's good to describe one of the cones, but we have two instead. We have a double cone, so we can extend this coordinate. We change its name to L, and then we make it positive and negative instead of only positive. So we go from the lower to the upper cone just by following L. So the induced metric in terms of L is this. And here is the summary of the geometries, or what is related to the geometry of the two cones in the Minkowski space, which is the Milne universe, and in the ordinary Euclidean space. What's more, well, these are the metrics I mentioned here. We have hyperbolic rotation instead of ordinary rotations, but in any case, the Laplacian has the same form except for this minus here. And this is the minus that gives us time in the hyperbolic liquid crystal wave equation that we solved. So we can use this in analogy with liquid crystals. So I mentioned a work by Chiang and Laventrovich that where they suggest you can make metamaterials with liquid crystals, with nematic liquid crystals, by doping with metallic nanorods. So if you here it's within let's say a glass container, so that you can impose the boundary conditions for the orientation. So you can choose the orientation of the molecules to be radial or circular. And when you put the nanorods here, they align, or they're supposed to align with the nematic order. So effectively, you get two geometries. In one is the Milne universe geometry, in fact, that cone in Minkowski space. And this one is a more peculiar one, because here time is circular. So this is more related to Gödel geometries in cosmology, but we have an application for that too. So we explored this a little bit in a paper a couple of years ago, where we found, for example, geodesics for this case here, which are these spirals. And a few other things in this article, but not important for here. This was also studied by these workers, where they proposed a solid-state metamaterial with different layers arranged like cylinders, or like slices of a cylinder like this, alternating metallic and dielectric. And in particular for this one, they found light rays will be kind of locked into a region. So there is a maximum radius where it can go, so it's circulating here. And they call this a hyperlens, an ideal lens of sorts. And we can have that in the liquid crystal, of course, and they mean something else. Yes. Oh yes, some people have done that. In fact, that the same Smolyaninov published a paper on that. The light cannot escape, yeah. In this case, they were not interested in analogies like that. They were just interested in optics and hyperlens, and so they didn't mention that. But of course, yeah, this could be related to something like that. Okay, here I come to the talk itself. So in the Milne universe, we have a cone in Minkowski space, which can be... Oh, okay, I have only three slides. Yeah. Okay, time-like geodesics. Here, I just mentioned what this means. This is classical trajectories or light rays, and the singularity is at t equals to 0, so it's this axis here. So if a particle is created here at the singularity, and with positive angular momentum, or the angle goes positive like this way, so it will go like that, and until the end of time. Or if it comes from the past, it will reach the singularity from here, but you see it will never reach it, in fact, in its proper time. In a polar plot, you see the curves goes like this, and they would go out like this. There's a blank dot there, just mention that, just to call the attention that the trajectories never get to the origin. So the wave part is similar, but this is a little bit interesting. The special relation is like that. The solution of this is in terms of Bessel functions of imaginary order that near the origin goes like this. And this, so as r goes to 0, log diverges, and this oscillates violently. So the wave function loses its phase. There's no meaning for a phase of the wave function here. So it's like the particle is annihilated before reaching the singularity and being recreated on the other side, like the classical picture shows here. And as a bonus, we got tachyons. Tachyons corresponds to this, which is the same trajectories they found, because they are space-like geodesics in the Milne universe, or time-like in this alternative geometry. So tachyons are funny because there's a beginning and an end of time for them. So if they are created of the singularity, they go towards the end of time and then go back to the singularity on the same part of the cone. If they come from the past, so they can go either counterclockwise or clockwise to the singularity. And so the trajectories are confined. So exactly what these people found there. Yes, I know. I'm finished. So I just put some conclusions you can read. So, and please, if you have any questions. Oh. I have some propaganda here. Louise is going to present a poster.